An object from another star system entered our solar system, raced past the Sun, and disappeared back into interstellar space. At first, it looked like a rare but ordinary comet. Then the James Webb Space Telescope examined the gases escaping from it. Hidden inside that light was something extraordinary, a chemical record of a world that may have formed as long as 12 billion years ago. That would make this visitor more than twice as old as the Sun. It may have existed before Earth, before our planets, and possibly before the star system that created it disappeared forever. Scientists did not find an alien spacecraft. They found something real, measurable, and in many ways even more valuable: a preserved fragment of an ancient planetary system. Its name is 3I Atlas, and the deeper scientists look into its chemistry, the stranger its story becomes. If you enjoy space discoveries explained without fake claims or exaggerated rumors, subscribe now. Because this is not a story about what someone guessed. It is a story written inside water, carbon, methane, and light. 3I Atlas was first reported on July 1st, 2025. It was detected by an Atlas survey telescope at Rio Hurtado in Chile. Atlas stands for the Asteroid Terrestrial Impact Last Alert System. Its telescopes repeatedly scan the sky, looking for moving objects that could approach Earth. Most of what they find belongs to our own solar system. This object did not. Astronomers measured its speed and calculated its path. The result was unmistakable. 3I Atlas was following a hyperbolic trajectory. That means its path around the Sun was open, not closed. It was moving too fast for the Sun to capture it permanently. It had arrived from interstellar space, and after one passage through our planetary neighborhood, it would leave again. This was only the third confirmed interstellar object ever discovered. The first was Oumuamua in 2017. It was small, faint, and already leaving when astronomers realized what it was. It showed no easily detected gas coma, so there was very little material for telescopes to analyze. The second was 2I Borisov in 2019. Borisov behaved more clearly like a comet. It released gas and dust, allowing scientists to study some of its chemistry. But it was faint, and the observing window was limited. 3I Atlas gave astronomers a much better opportunity. It was discovered months before its closest passage around the Sun. It was bright. It was active, and it appeared at a time when humanity had access to instruments that did not exist when Oumuamua was discovered. At discovery, 3I Atlas was traveling at about 221,000 kilometers per hour. As it fell deeper into the Sun's gravity, it accelerated. Near its closest point to the Sun, its speed reached about 246,000 kilometers per hour. It never threatened Earth. Its closest distance from our planet was roughly 270 million kilometers. That is nearly twice the distance between Earth and the Sun. On October 30th, 2025, the comet reached its closest point to the Sun. Even then, it remained about 210 million kilometers from our star, just outside the orbit of Mars. But distance did not stop the sunlight from changing it. As the comet warmed, frozen material began turning directly into gas. This process is called sublimation. The escaping gas lifted dust and ice away from the nucleus, forming a bright cloud around it called a coma. For astronomers, that coma was not visual decoration. It was evidence. A dormant object keeps most of its composition locked inside. An active comet releases part of that composition into space. Every molecule in the coma carries information about the ice, dust, and rock that formed around another star. That is why 3I Atlas became so important. It was not simply passing through our solar system. It was opening itself in front of our telescopes. The Hubble Space Telescope helped reveal the dust surrounding its icy nucleus. But measuring the solid nucleus was difficult, because the coma made the object appear brighter and larger than it truly was. Hubble observations placed the diameter somewhere between about 440 meters and 5.6 kilometers. That is a wide range, but the uncertainty itself is important. No honest measurement can separate the nucleus perfectly from the bright material around it yet. Claims that give one exact size create a false sense of certainty. The real breakthrough did not come from measuring the comet's shape. It came from reading its light. The James Webb Space Telescope observes mainly in infrared wavelengths. Human eyes cannot see infrared light, but molecules absorb and emit it in specific patterns. Those patterns work like chemical fingerprints. By splitting the comet's light into a spectrum, Webb could identify gases that no ordinary photograph could reveal. During observations made while 3I Atlas was still approaching the Sun, Webb found that its coma was dominated by carbon dioxide. The ratio of carbon dioxide to water was about 8:1. That was among the highest ratios ever measured in a comet. It stood well above the normal trend seen in most long-period and Jupiter family comets from our own solar system. Webb also detected water, carbon monoxide, carbonyl sulfide, water ice, and dust. This did not mean the comet was impossible or unnatural. It meant that the mixture of material inside it was different from what astronomers usually see close to home. There are several possible reasons. The comet may have formed near a different ice boundary in its original planetary disk. Its surface may have been heavily processed by radiation during its long journey through interstellar space. Or heat may have reached some layers more easily than others, allowing carbon dioxide to escape while much of the water remained trapped. At that stage, the carbon dioxide was already a major clue. But it was not the final surprise. After the comet passed the Sun and began moving outward, Webb observed it again in December 2025. This time, scientists used Webb's mid-infrared instrument to examine a broad range of wavelengths. The spectra revealed water vapor and carbon dioxide. They also showed a specific signal from atomic nickel. Then researchers found methane. It was the first direct detection of methane in an interstellar object. Methane is a simple molecule made from carbon and hydrogen. On Earth, it can be produced by living organisms, but it can also form through completely non-biological chemistry. Detecting methane in a comet is not evidence of life. Its importance here came from what it revealed about the comet's layers. The methane did not appear to rise in exactly the same way as the water. Researchers found evidence of a delayed release. One explanation is that methane near the outer surface had been depleted or altered during the comet's extremely long exposure to cosmic radiation. As sunlight warmed the object more deeply, fresher material beneath the surface began to vent. That means Webb may have sampled ice that had remained protected inside the comet for billions of years, not untouched in an absolute sense. Comets can be fractured, heated, and chemically changed. But this subsurface material may still preserve a far older record than the radiation-processed crust above it. NASA's SPHEREX telescope saw another part of that transformation. In August 2025, SPHEREX observed a coma rich in carbon dioxide, with smaller amounts of carbon monoxide and water. By December, the comet had brightened dramatically. Its coma had become more active and chemically diverse. SPHEREX detected water, carbon dioxide, organic molecules such as methanol, cyanide-related material, and methane. It also saw evidence that the comet was throwing off rocky grains and unusually large particles. This delayed eruption makes physical sense. A comet receives its strongest sunlight near its closest point to the Sun, but heat does not instantly reach deep below the surface. It takes time to move through the outer layers. The comet can therefore become more active after its closest approach, once heat finally reaches buried ice. 3I Atlas behaved like an ancient frozen container, slowly opening from the outside inward. First came material that was easy to release. Then came a richer mixture from below. But the most important discovery was still waiting inside the isotopes. An isotope is a version of an element with the same number of protons but a different number of neutrons. The chemistry is similar, but the mass is slightly different. Those small differences matter because the ratios of isotopes can preserve information about temperature, radiation, and the chemical environment in which material formed. Scientists used Webb to measure the isotopic composition of water, carbon dioxide, and carbon monoxide in the comet's coma. They found that its water contained an extraordinary amount of deuterium, also known as heavy hydrogen. The measured ratio of deuterium to ordinary hydrogen was close to 1%. That may sound small, but it was more than an order of magnitude higher than the levels measured in known comets from our solar system. The carbon isotope ratios were also unusual. 3I Atlas contained much less of the heavier carbon-13 isotope relative to carbon-12 than scientists normally see in our solar system, nearby interstellar clouds, or young planet-forming disks. These were not random details. Together, they pointed toward an extremely cold and chemically primitive birthplace. The heavy hydrogen suggests that much of the comet's water ice formed at temperatures below roughly 30 Kelvin. That is colder than -240 degrees Celsius. The unusual carbon signature suggests that the material formed in a low metallicity environment. In astronomy, metal does not only mean iron or nickel. Astronomers use the word for nearly every element heavier than hydrogen and helium. A low metallicity environment contains less material created by earlier generations of stars. That points backward in cosmic history toward a younger Milky Way. When researchers compared the isotope measurements with models of how the galaxy's chemistry changed over time, they reached an astonishing possibility. 3I Atlas may have formed as long as 12 billion years ago. Our Sun is about 4.6 billion years old. Earth is roughly the same age. If the estimate is correct, the comet could be more than twice as old as the entire solar system. It may have assembled during an era when the universe was producing stars at a far greater rate than it does today. Its original star may have formed in a cold, dense cloud containing a different balance of elements from the cloud that produced our Sun. Around that star, dust and ice gathered inside a planet-forming disk. Some of the material built planets. Some remained as small frozen bodies. At least one of those bodies was eventually thrown away. A close encounter with a planet, another star, or a complex gravitational disturbance may have accelerated it beyond the grip of its home system. From that moment, it became a wanderer. It crossed the space between stars with no permanent sun and no stable home. Its surface was exposed to cosmic rays. Its outer chemistry changed. A radiation-processed crust may have formed around older ice. The journey could have lasted billions of years. Then, in 2025, its path happened to cross ours. For a few months, sunlight warmed it. Ancient gases escaped. Telescopes built by a civilization on a small planet collected those gases as patterns of light. That is the true scale of this discovery. Humanity did not travel to another planetary system. A fragment of another planetary system came to us. There is an important scientific warning here. The age is not stamped on the comet like a date on a document. No telescope watched it form. Earlier estimates based on its motion through the galaxy allowed a very broad age of roughly 3 to 11 billion years. Tracing an exact path backward over billions of years is nearly impossible because repeated gravitational encounters make the motion chaotic. The newer estimate comes from isotope ratios and models of galactic chemical evolution. It offers stronger evidence for an ancient origin, but it is still an inference. The correct statement is not that scientists proved the comet is exactly 12 billion years old. The correct statement is that its chemistry is consistent with formation in an extremely cold, old environment, and models indicate it may have formed as long as 12 billion years ago. That distinction does not weaken the discovery. It makes it credible. A separate team using the European Southern Observatory's Very Large Telescope measured carbon and nitrogen isotopes in cyanide molecules around the comet. Those measurements also pointed toward an old, low metallicity star system. Independent instruments, different molecules, and different research teams were beginning to tell the same story. 3I Atlas was not merely foreign. It may have been ancient even before the Sun existed. This is also where online rumors need to be separated from the evidence. Because the comet came from outside the solar system, moved quickly, and showed unusual chemistry, some people claimed it might be artificial. But unusual does not mean engineered. The object has an icy nucleus. It releases gas and dust as sunlight warms it. It has a coma. Its small changes in motion are compatible with normal cometary outgassing. Its molecules can form through known natural processes. Targeted radio searches did not find a credible technological signal associated with it. No single observation can prove every negative claim. But there is currently no reliable evidence that 3I Atlas is a spacecraft, a probe, or an artificial object. Everything measured so far is consistent with a natural interstellar comet, and the natural explanation is already remarkable. Carbon dioxide does not need aliens to be important. Methane does not need life to become a scientific first. Nickel does not need a machine to reveal chemistry from another star system. Heavy water does not need a conspiracy to show that this object formed in a cold environment unlike our own. The real story is not that scientists found technology. The real story is that they found history. Every star system begins with a cloud of gas and dust. Gravity pulls part of that cloud together. A star ignites near the center, while a disk of leftover material circles around it. Inside that disk, grains collide. Ice freezes. Rocks grow. Planets begin to form. The exact result depends on temperature, radiation, location, and the elements available at that time. By studying 3I Atlas, astronomers can test whether planet-forming chemistry elsewhere resembles the chemistry that built our own solar system. The answer appears to be both yes and no. The comet contains familiar ingredients: water, carbon dioxide, carbon monoxide, methane, methanol, dust, and metal atoms. But the proportions and isotope ratios are different. The same basic ingredients can be mixed under very different conditions. That matters for the study of planets, atmospheres, and the distribution of organic chemistry across the galaxy. It also turns an interstellar comet into a tool for galactic archaeology. Archaeologists reconstruct human history from objects left behind. Astronomers can reconstruct part of the Milky Way's chemical history from an object that preserved material from an ancient era. 3I Atlas may carry evidence from a time when our galaxy contained fewer heavy elements and star formation was much more intense. One small comet can therefore connect three enormous stories: the birth of planetary systems, the chemical evolution of the Milky Way, and the long journey of material between the stars. There is also a lesson in timing. Telescopes have existed for only a few centuries. Instruments capable of measuring detailed infrared spectra from a faint interstellar comet have existed for only a fraction of that time. 3I Atlas may have traveled for billions of years, yet it crossed our solar system during the narrow period when humanity could recognize its origin and decode its chemistry. If it had arrived before modern astronomy, it might have appeared as nothing more than a faint comet. If it had arrived in 2017, the James Webb Space Telescope would not yet have been in space. Instead, it appeared after Webb and SPHEREX were ready, while Hubble was still operating, and while observatories around the world could coordinate their measurements. NASA spacecraft near Mars also observed it. Other missions across the solar system gathered additional images and data. Ground-based telescopes tracked its motion and gases. Each instrument contributed a different piece of the same puzzle. No single telescope told the entire story. Hubble constrained the nucleus and dust. Webb identified molecules and isotope ratios. SPHEREX followed the changing activity. The Very Large Telescope measured additional isotopes. Radio observatories studied molecules at longer wavelengths and searched for unusual signals. Together, they turned a moving point of light into the chemical portrait of an ancient world fragment. 3I Atlas is now heading outward. The sun's gravity is slowing it back toward the speed it had before entering. But it will not stop. It will not turn around. its path remains open. The comet will continue into interstellar space, carrying away material that our telescopes briefly watched escape. Scientists will continue analyzing the data long after the object becomes too faint to study. New results may change the details. The estimated size may narrow. More molecules may be identified. Better models may refine its age and birthplace. That is how science works. The story becomes stronger as uncertainty is measured, claims are tested, and different teams compare results. Future sky surveys are expected to find more interstellar visitors. The discovery of 3 such objects in less than a decade does not by itself tell us exactly how common they are. Detection methods have improved rapidly, and many smaller or darker objects may pass unnoticed. But the next discovery may come earlier in its approach, giving astronomers even more time to prepare. One day, a spacecraft may even be positioned to intercept an interstellar object before it escapes. Until then, light is our sample container. And 3I Atlas gave us an unusually rich sample. It arrived with a carbon dioxide-dominated coma. It released water, carbon monoxide, methane, methanol, dust, and nickel. Its methane may have emerged from material protected below a radiation-altered surface. Its heavy water suggests formation at extremely low temperatures. Its carbon isotopes point toward an old, chemically primitive environment. And together, those clues suggest that this comet may have formed up to 12 billion years ago, long before the Sun and planets existed. That is what the James Webb Space Telescope truly found. Not a photograph of an alien machine, not proof of life, something quieter, older, and more profound. A chemical memory from another star system, a frozen survivor from the early Milky Way. And for one brief moment, it passed close enough for humanity to read its story. If this discovery changed the way you think about comets, subscribe to the channel. Then tell me in the comments, what is more surprising to you? The comet's possible age, its unusual chemistry, or the fact that humanity was here at exactly the right time to detect it? Share this video with someone who enjoys real space science without the fake hype. And I will see you in the next one.